Google's Willow is the most powerful quantum processor on the market, or at least it was. A recent technological breakthrough from China unveiled the Zu Changji 3.0 processor, establishing a new quantum computational advantage. If the Chinese scientists are to be believed, this new processor claims to match, if not surpass, Willow's capabilities. But is this a leap forward in technology or a game of hype? And why does this quantum battle matter for the future of AI, global security, and power? Let's uncover the secrets behind this quantum arms race together very quickly. China's Zu Changji 3.0 is another quantum chip, also with 105 qubits. In tests, it completed a computation in a few hundred seconds. This task would take the frontier supercomputer approximately 6.4 billion years. The Zu Changji chip was developed by a team of researchers at the University of Science and Technology of China, and it was released in December 2024. The chip's single qubit fidelity measures 99.9%, while the 2-qubit fidelity is around 99.62%. Also, the chip's readout fidelity is around 99.18%. If you're wondering what all of this is, then here's a simple explanation. Imagine you're tossing a basketball into a hoop. Single qubit fidelity is like measuring how often the ball goes through the hoop exactly as planned without bouncing off the rim or missing. If you have a high single qubit fidelity, it means your aim and throw are nearly perfect every time. In quantum computing, this precision ensures qubit operations, like flips or rotations, happen as expected, which is essential for accurate computations and building reliable quantum systems. This chip has 105 qubits, matching Google's Willow processor. In tests, Zu Changji 3.0 solved complex problems in seconds. It might seem like any other achievement, but this one actually shows China's growing strength in quantum computing. It also increases competition in this field. With Zu Changji 3.0, we move closer to practical quantum computers. Right now, the reason Zu Changji 3.0 is so revolutionary is because it can solve very complex mathematical problems that traditional supercomputers struggle with, such as simulating quantum systems or solving optimization tasks. It excels in quantum supremacy experiments, where it demonstrates solving problems that would take classical computers billions of years. These applications highlight its ability to smash that like button, just like you should if you haven't done so already. But no, in all seriousness, they highlight Zu Changji's ability to perform tasks like simulating molecules for drug discovery, optimizing logistics, or improving machine learning algorithms, showcasing the power of advanced quantum computing. These machines could revolutionize industries by solving problems beyond the reach of today's computers. But how does it compare to the current fastest quantum chip in the world, Willow? The race between Willow and Zu Changji 3.0 isn't just about speed, error correction, or quantum computers. It's all about quantum supremacy. There's a new race happening right now between China and the US, and it's not about arms, it's about quantum computers. Willow and Zu Changji might be quantum chips, but they actually represent a new frontier of battle. Before we tell you more about that, let's see how the two chips compare. Both chips have 105 qubits inside, which is the highest number of qubits in superconducting quantum devices. Because they're considered the largest superconducting quantum processors to date, it shows the very rapid progress of quantum hardware. Like I said before, Zu Changji prides itself on high operational fidelities, which is a very important metric when it comes to showing the accuracy of quantum operations. To achieve this, the Chinese researchers had to refine the circuit parameters, enhance the electric field distributions, upgrade the attenuator configuration, and so on. The hardest of all these improvements had to be the improvement of the entire chip fabrication process. That's probably why the Zu Changji has an average Pauli error for single qubit gates that's around 0.1%, while the error for the I-swap-like gates is decreased to 0.38%. And that's just the tip of the iceberg. You see, the scientists improved the quantum chip's readout performances. This way, the chip can accurately measure the state of qubits. It uses strategies like increasing the coupling strength between qubits and readout resonations, or they could tune the line widths of the readout resonators. Also, they can even optimize the bandpass filter design, which simply protects each qubit from the Purcell effect. On the other hand, Google's Willow quantum chip focuses on something completely different. For years now, the quantum computing field has been plagued by error correction. No matter how big of a chip companies built, it was useless. They couldn't use all the qubits because of the high error rate. When they increased the number of qubits, they also increased the error rate in that chip. Google's Willow chip addresses quantum error correction by implementing a process called below threshold error correction. This means that as the number of qubits increases, the error rate decreases, which is a major step forward. Willow uses surface code techniques, which involve grouping physical qubits to form logical qubits. These logical qubits can detect and correct errors without disrupting the overall computation. This approach makes the system more reliable and scalable, which is critical for building practical quantum computers. So, you can think of Google's Willow chip as a team of people building a sandcastle. Each person works on one part, but mistakes happen. To fix this, they work in groups where others check for and fix errors. As more people join, the team becomes better at catching mistakes and keeps the sandcastle strong and accurate. This teamwork ensures the castle, the computation, remains stable, even if individual workers occasionally slip up. This is how Willow's error correction works. And while Zu Changji 3.0 couldn't even come close to the same error correction levels, they have said that in future models, they will try to implement Google's technology in their new chip. According to China's benchmarks, they expect to reach the distance of 7 surface codes in just a few months. If they do, China will have crossed a very important benchmark in error correction. But why are the US and China competing on who can build the fastest and strongest quantum computers? Why does it even matter? The United States and China are leading a global race in quantum computing, each excelling in different areas. The US holds a significant lead in quantum computing, particularly in hardware and practical systems, thanks to its private sector technology innovators, government labs, university researchers, and collaborating allies. In contrast, China leads in quantum communication and matches the US in quantum sensing, focusing on transforming proven quantum ideas into products. This competition has profound implications for global technology and security. Because quantum computers are very powerful, they can solve certain mathematical problems much faster than classical computers. One of the most worrying threats is that powerful quantum computers could break widely used cryptographic systems like RSA encryption. These systems secure sensitive information, including government communications, military data, and financial transactions. If China were to develop a sufficiently powerful quantum computer, it could decrypt classified information, which could undermine national security. And it's not just about stealing your iMessage texts. Think about the far-reaching implications of such a computer. Cybersecurity as we know it could be gone. Espionage and information warfare could take on a completely different meaning. Not to mention, quantum computing could accelerate the development of artificial intelligence, and if China were to harness quantum-powered AI, it might lead to breakthroughs in autonomous systems, robotics, and other technologies that could outpace US capabilities in fields like defense and manufacturing. But while China and the US are chasing each other on the quantum field, where is Europe in all of this? Europe is actively pursuing quantum technologies through initiatives like the Quantum Technologies Flagship, a long-term research and innovation program aiming to position Europe at the forefront of the second quantum revolution. With a budget of 1 billion euros over 10 years, the flagship supports hundreds of quantum researchers, fostering collaboration among research institutions, academia, industry, enterprises, and policymakers. Additionally, the EU's Digital Decade strategy aims for Europe to have its first supercomputer with quantum acceleration by 2025, paving the way to being at the cutting edge of quantum capabilities by 2030. In summary, while the US and China are currently leading the quantum computing race, Europe is trying to make significant investments and become a key player in the field. Unfortunately, $1 billion over 10 years is basically nothing in the quantum computing game, and Europe might need to widen its pockets if it wants to remain competitive. Here's another video AI enthusiasts loved watching. This is AI Exposed, demystifying the world of artificial intelligence, one video at a time.